Let's now take a look at different forms of wireless communication. Now, the first question we might ask about wireless communication is, why do we need wireless communication? And the answers to that sort of, revolve around the notions of mobility and portability. What we mean by this is mobility basically means that you should be able to take a particular device and move around with it. Portability is an extension of that. It says you can actually take it and move it to a completely different place and have it work somewhere else. They are related terms. You may also find that you want to establish a network over some kind of long range or a long distance, right, or something that is completely ad hoc and temporary, right. And in both these scenarios, it may turn out that actually putting wires across that distance or in such a manner is not feasible or realistic, right. In which case, maybe if there is a means by which you can communicate wirelessly without needing physical wires, that opens up a very interesting mode of communication. Now, there are many forms of wireless, one of which would simply be, standing somewhere and waving to another person. In principle, that's a form of wireless communication. It's by line of sight, right? And the way that you're communicating is there is actually a visual signal which is using light frequencies, right, the light wavelengths, in order to communicate information. What we usually mean though when we talk about wireless communications in this context is that we are using radio frequency signals, radio frequency being a part of the overall electromagnetic spectrum. Light is also a part of the electromagnetic spectrum, so are X-rays, so are gamma rays, so are various kinds of radio waves, all the way from AM bands to FM, and then the higher frequencies VHF, UHF and so on, to the ranges where we are typically looking at things like in the low gigahertz ranges of frequencies. Now, this electromagnetic spectrum is related to the fact that the spectrum is a measure of how the frequency is used, right? We are basically translating from the time domain into the frequency domain. At some point you would need to do a course in signal processing in order to fully grasp the the meaning of those terms. But effectively what it means is that there is a way by which you can radiate energy in the form of these waves, and that energy can then be picked up at a remote source and translated back into an electrical signal. Now, there's a reason why 2.4 gigahertz and 5 gigahertz are very common frequencies that you will encounter in many of the communication protocols that we have. One of them is related to the fact that these wavelengths are now short enough that the kind of antennas you need in order to use them are on the scale of what portable devices look like. So they sort of match well with the kind of circuits and systems that you can build for portable devices. The other is, these are what are called unlicensed bands of the spectrum. The spectrum use itself is very tightly controlled at national and international levels, because there are a number of defense and security related applications that revolve around the electromagnetic spectrum use, right? So these bands have been sort of let out as saying, okay, we will give them out, they are free for anybody to use, and a lot of the communication signals have therefore evolved around those bands. The flip side is a lot of protocols have evolved around that, which also means there is a lot of interference in those bands. So what I'm going to do at this point is just very high level sort of breeze through a few examples of different kinds of wireless communication systems, because once again the purpose over here is not really to deep dive into any one of them in terms of how they work. It is only to sort of know their different properties so that you can sort of have an idea of where one might be useful as opposed to another. One thing to keep in mind is almost all of these have some notion of the networking protocols that we talked about earlier built into them. So there is some notion of addressing, and most of them have compatibility at some level with the IP, the Internet Protocol. What I mean by that is the base Wi-Fi by itself only talks about how to transfer packets of information, but it's possible to build an IP layer on top of that, which means that in those packets you put in the IP address, you put in the routing information and so on, and you can therefore use it to directly communicate with, let's say, an Ethernet device. So that is the power of the internetworking protocol, the IP, right, which basically says that there could be one device which is on Wi-Fi another one which is on Ethernet, but as long as both of them can encapsulate information into IP packets, they can communicate between each other, and there can be just one device somewhere in the middle that has a wireless interface on one side and a wired interface on the other side, and can basically switch packets between the two sides. And that basically is what a Wi-Fi router looks like, right? So Wi-Fi by itself stands for wireless fidelity. I'm not entirely sure what that means, but it's wireless radio communication, that's all. It is the technical term for it is what's called the IEEE 802.11 standard, of which there are many subdivisions, right, variants. 11AC is probably the one that is probably the most common at this point in time. If you were to go pick up a router and you are looking for a good fast router and not very expensive at that, you would probably get something in the 11AC class at this point. But each of these variants has different kinds of properties about the range of the range that it can cover, and also the speed that it can achieve. It works in a combination of the 2.4 gigahertz and 5 gigahertz RF or radio frequency bands, which are in turn divided into a number of channels. And there are many interesting properties, including the fact that these bands undergo attenuation. They cannot safely pass through walls, or rather they can, but the signal strength on the other side of the wall will be much lower than what it was on the source side. Unlike light, which simply cannot pass through a wall, these frequencies can, but with severe attenuation. They also get attenuated by greenery. So the interesting thing is that if you actually have trees in your path and you're trying to use this outdoors, you might find that it doesn't work as well as you would like. Right? One very important aspect of all of these things is, keep in mind that with any wireless communication, you are actually just radiating information, and you don't have any way of knowing who or what is going to be listening in on that information. So unless you take steps to encrypt or have some kind of security, which basically sort of scrambles the information that you are sending with some key that's known only to you and to the recipient, you are basically sort of broadcasting information for everyone to listen to. Okay, so there are many different forms of security that are baked into the Wi-Fi standards, and some things like WEP, for example, are outdated at this point. They are deprecated, saying that they are simply not secure enough for normal use, and you shouldn't be using them. It is always good to be aware of those what the current sort of standards are. It's a trade-off between how complex it is to implement the security protocol versus how much security it gives you. So WPA Enterprise, for example, is probably a much higher degree of security than even just WPA2, but on the other hand requires a lot more infrastructure in terms of the servers and so on to support it. Wi-Fi is typically used in many contexts: residential, commercial, and primary kinds of applications would be computers, smartphones, and similar kinds of devices. The range over which it works would be either inside a room or maybe at best inside a small building, right? It's not really meant for outdoor applications at all. Now, another example of wireless communication is Bluetooth, which once again you have most likely heard of in the context of something like maybe a Bluetooth headset, right? And that is one of the more common areas where it is actually used. It was designed in fact for the PAN, the personal area network, right? So even though it technically has a range of up to 100 meters, it is best suited for really short range in the immediate neighborhood of what a single person is doing. And what that means is there are also variants called Bluetooth Low Energy that are designed explicitly for minimizing the power consumption and are very efficient, because keep in mind that unlike an electrical signal on a wire where you have to change the voltage levels on a wire, in the case of RF you actually have to radiate, and that radiated power is sort of spreading out in all directions. Only a very small part of it is reaching your destination. So the amount of power that you are radiating versus the amount that is actually required for pickup at the other end can be orders of magnitude different, which in turn means that potentially your wireless communication can be power hungry and can be problematic for battery powered devices. Now, Bluetooth has its own forms of security. It is primarily meant for the personal area. So, the most common form of security that you are likely to come across is the pairing, right? There will be a number that it shows on a screen and some other number, and you have to sort of verify that they are the same. And it's a trade-off once again between convenience in terms of how you establish the security versus how strong of a security guarantee that you can provide. The applications, as I said, the most common ones today are probably earphones and headsets, and of course Bluetooth speakers, but also wearables, watches, rings, various kinds of things that are doing medical monitoring and so on. Yeah. Zigbee is a standard which is not as popular or common as Bluetooth and Wi-Fi. It is based on the IEEE standard 802.15.4. It uses some kind of a mesh topology where it can connect a large number of devices and has the potential for actually achieving low latency communication between those devices. It's primarily designed for low power, and the main target application areas for Zigbee are around the domain of home automation. That's the one where it actually had the most success, and also for certain things such as medical device data collection. Now, on a practical basis, if you are asked to design a new system, it would be a question of why do you want to use something like Zigbee as opposed to something like Wi-Fi or Bluetooth, which Wi-Fi has significantly higher data rates. Bluetooth has other kinds of advantages in terms of low power and so on. So, is there really a need for another protocol? That there are specific use cases where Zigbee really shines, and it's up to you to sort of figure out whether it makes sense for your application and see where it might fit. LoRa is a slightly different thing. I mean, it's not trying to solve the same problem as, let's say, Wi-Fi or Bluetooth. It is explicitly trying to target long range wireless communication, right? And by long range we mean possibly even tens of kilometers, right? You can, in relatively less populated, or more importantly areas of less construction of buildings, you could probably even go for something like 15 to 20 kilometers, or in urban areas with relatively more buildings, it could still manage something like maybe 2 kilometers or even a bit more than that. It's designed with the idea of being extremely low power in mind, and it's ideal for battery operated devices. It uses some kind of a star of stars network, which basically means you have end devices that are all communicating with one hub out here, which in turn sends its information somewhere else, and you can see that there is a high level star which in turn has smaller stars around it, right? The point is that you are sort of aggregating data at each of these points and then sending them to higher levels till you get to your final collection stage. Now, this is just one of the possible network topologies. So, what kind of applications can you think about? You are looking at long distance, but the combination of long distance and low power typically means that your data rates are not going to be anywhere close to what you would expect with, let's say, Wi-Fi, right? So, there could be agricultural applications, smart cities, basically sensors that are not generating huge volumes of data, but need to be sort of operating in remote places for long periods of time. So, LoRa is one of those things which has its own sort of niche within which it fits, and it makes perfect sense in those kind of applications. And of course, there is also the GSM, the Global System for Mobile Communication, which has basically evolved, and today we are probably looking at what most likely you will be looking at 5G, the 5th generation of GSM. It was designed, of course, primarily for general human mobile communication, but was then also adapted for IoT kind of applications. And in particular, the latest iteration 5G has something called the narrowband IoT, narrowband Internet of Things, which is a particular variant of the protocol that is well suited for communication with IoT devices. There are a couple of nice aspects. One is the fact that security is taken care of by a different means. You don't have to sort of share a key between things. There is a central notion of a SIM, a subscriber identifier module, which basically is able to verify your identity to a central provider, and it can cover wide ranges. You can do possibly even kilometers, but it requires that infrastructure support. You can only sort of communicate when there is a tower within a reasonable range of where you are, right? So you are unlikely to get, like, any kind of a signal maybe 5 kilometers or 10 kilometers away from a tower. But if you do have the presence of towers, you can just make use of that existing infrastructure and not have to put in any sort of hubs or repeaters of your own in order to get communication. So if you want to deploy one sort of sensor or IoT device which is quite remote from everything else that you have, but is within range of some cellular tower, this would be a perfect way of solving that problem. So to summarize, let's quickly look at a few of the differences between wired and wireless protocols. Wired protocols really shine when it comes to reliability. You are basically talking about wires where you can physically inspect them and be sure that as long as the wire is in place and is not damaged, you are going to get good communication. They can also go to really high speeds. Security is sort of implicit because unless somebody has physical access to the wire, they can't really tap what you are communicating. And although there is some notion of crosstalk in wires, you don't really have much of a notion of interference. On the other hand, they typically tend to cost more to actually lay wires, right? They are also relatively inflexible, meaning that once you have mapped out and decided where your wires go, let's say you're suddenly asked to scale and add more machines, that becomes not so easy to do. It can also lead to clutter, which is just managing different wires all over the place, and you also need power in order to run all the switches and routers that are present all over the system. Wireless, on the other hand, the biggest sort of plus point is just the convenience, right? And also the ease of setup. Nowadays, at least, it's fairly easy to even connect to a new wireless network and so on. They are scalable because you can sort of add repeaters or extenders in order to increase the range, and it's probably easier, at least at an initial level, to scale out to add more devices than with a wired network. Very little clutter. You don't actually have physical wires that you need to deal with, and there are low power modes that can be used for even battery operated devices. Now on the flip side of that, wireless is fundamentally a shared medium, meaning that everyone is broadcasting into the same space, and unless you take specific care to create channels and make sure that people don't interfere with each other too much, it can cause so much interference that communication starts to become really bad. Security is a problem because it's a shared medium. Unless you explicitly take some steps to encrypt, you simply are opening up your communication for everyone to observe. Speed, in order to get high speeds, you need to have like a large bandwidth, which in turn opens you up to other problems of interference and so on, which are much less of a problem in the case of wired networks. Right? Reliability is also an issue. Something as simple as rain can mean that a wireless link that goes outdoor gets disrupted because water absorbs 2.4 gigahertz radiation, right? And therefore you sort of have a poor quality of connection. And even though the low power modes mean that you can run on battery, it now introduces a new dependency. You need that battery, and it in turn, the life of the battery becomes one of the concerns that you have to take into account while designing your system.